Introduction to Solutions in Aqueous Reactions, Acid-Base Reactions. In this tutorial, we will be looking at the Bronsted-Lowry definition of acids and bases, strong versus weak acids and bases, neutralization reactions, and worked examples specifically focusing on strong acid, weak base scenario, weak acid, strong base scenario, weak acid, weak base scenario, and finally, strong acid, strong base scenario. A Bronsted-Lowry acid is defined as a molecular compound that is able to donate a hydrogen ion, otherwise known as a proton, when dissolved in water, thereby increasing the concentration of the hydronium ions. A Bronsted-Lowry base is defined as a solution containing a base that creates additional hydroxide ions, causing the concentration of hydroxide ions to increase. There are a few strong acids that you definitely need to know in this course, the formulas and the names. They are HCl, which of course you know is hydrochloric acid, HBr, which is hydrobromic acid, HI, which is hydroiodic acid, HNO3, which is nitric acid, H2SO4, which is sulfuric acid, HClO4, which is perchloric acid, HClO3, which is chloric acid, and HiO3, which is iodic acid. In terms of the AP chemistry exam, these are the acids that I encourage you to be most familiar with in terms of strong acids. When we talk about strong bases, these are a little bit more straightforward. LiOH, lithium hydroxide, NaOH, sodium hydroxide, KOH, potassium hydroxide, RbOH, rubidium hydroxide, CSOH, cesium hydroxide, CaOH2, calcium hydroxide, SrOH2, strontium hydroxide, and BaOH2, barium hydroxide. So you'll see that these strong bases are composed of the group 1 metals along with the heavier group 2 metals. In terms of weak acids, the ones that I would encourage you to know the best are H2SO3, which is sulfurous acid, H2CO3, which is carbonic acid, HF, hydrofluoric acid, HC2H3O2, which is acetic acid, H3PO4, phosphoric acid, HCN, hydrocyanic acid, HCHO2, formic acid, and H2C2O4, which is oxalic acid. Finally, the weak bases. The ones that I suggest that you know the best are NH3, which is ammonia, CH3NH2, methylamine, CO3-2, which we know as the carbonate ion, along with HCO3-1, the hydrogen carbonate ion, and S-2, the sulfide ions. And for each of these ions, we'll look at very specific situations where you can identify these as weak bases. A neutralization reaction is a reaction where a solution of an acid and a base are mixed to produce water and an ionic salt. So a classic example here would be hydrochloric acid with sodium hydroxide produces water and sodium chloride. Let's look at some more examples of neutralization reactions. The first scenario that we're going to look at is a solution of hydrobromic acid and magnesium hydroxide are mixed together. The key thing that you need to be aware of is that hydrobromic acid is a strong acid, while magnesium hydroxide is a weak base. So now we have to go back to our previous very long video on net ionic equations and remember a couple of quick things. So the first thing I'm going to do is write out my correct formula for my reactants. So HBr plus MgOH2. And when I do a double replacement reaction on this, The hydrogen is going to go with the hydroxide, which is going to give me water, H2O, because we know in all of these water is going to be a product. And then I have Mg plus 2 and Br minus 1 to give me MgBr2. The next thing that I'm going to do is balance this. So I have 2 bromines over on my product side, so I'm going to put a 2 in front. And then the last thing that I need to do is put a 2 in front of the H2O. And then looking over everything, I think I'm pretty good to go. So I know HBr is a strong acid, and I know that magnesium hydroxide is a weak base. Water is a liquid, we're just going to leave that alone, but it is a liquid, so we're not going to touch it. And then MgBr2 is a strong electrolyte, so that's going to fully dissociate. Now that I know that, I'm going to break these up into a complete ionic equation. So 2H plus 1 plus 2Br minus 1. MgOH2 is a weak base. That is not going to be broken apart. Do not separate your weak acids and weak bases into ions. Don't do it. Don't do it. And then I have 2H2O, that's a molecular compound, not going to touch that, plus, and then MgBr2 is a strong electrolyte, so Mg plus 2 plus 2Br minus 1. Excellent. The last thing that I need to do here is identify any spectator ions that I might have and cross those out. So the only spectator, and I only have one here, is the 2Br minus 1. So I'm going to cross it out there and there. And then the final thing that I am going to do is rewrite my net ionic equation. 2H plus 1 plus MgOH2 arrow 2H2O plus Mg plus 2. And that is my net ionic equation between a strong acid and a weak base. Let's look at another example. Acetic acid and potassium hydroxide are mixed. Okay, so my molecular equation for acetic acid is HC2H3O2 plus potassium hydroxide, which is KOH arrow. This is going to be a double replacement reaction where I know one of my products will always be water. And then I have K plus 1 with C2H3O2 minus 1. The plus 1 and the minus 1 are going to cancel each other out. So K C2H3O2. And if I look through this, I actually don't think I need to balance it at all. I think it is already balanced, so that is great. HC2H3O2 is a weak acid, so I am not going to touch that in my complete or net ionic equation. KOH is a strong base. H2O is a liquid, so I'm going to leave that alone. And then KC2H3O2 is a strong electrolyte. So that is going to fully dissociate. So when I write my complete ionic equation, I'm going to leave my weak acid alone. So HC2H3O2 plus K plus 1 plus OH minus 1 yields water, H2O, plus K plus 1 plus C2H3O2 minus 1. Excellent. My next task, of course, is to look through for my spectator ions, and I believe the only spectator ion I have here is K plus 1, so I'm going to cross that out. I'm going to leave my weak acid alone. And then the last thing that I'm going to do is to write my net ionic equation. So HC2H3O2 plus OH minus 1 yields H2O plus C2H3O2 minus 1. And that is my net ionic equation between a weak acid and a strong base. My next example is hydrocyanic acid and ammonia are mixed. Okay, well, hydrocyanic acid is HCN plus ammonia is NH3. Now, this is a very interesting situation because when I look at this, I know that HCN, well, that's a weak acid. And NH3 is ammonia, and that's a weak base. Now, they will react together, but for the most part, in solution, these are going to remain molecules of HCN and NH3. So I'm going to put a double arrow here, stressing the fact that most of the time, these are going to remain as reactants. But HCN will still act as a Bronsted-Lowry acid, and it will still donate this hydrogen over to the ammonia. And now you might be saying to yourself, well, how does that work? Because nitrogen can only have 3 bonds. Well, if you remember, if you think about the structure of ammonia, there's my covalent bonds between the nitrogen and the hydrogen, and then you know that nitrogen has a lone pair up on the top. When HCN donates that hydrogen ion to the ammonia, we form the ammonium ion. So that H plus 1 snuggles up close to this lone pair right here, which I'm just going to circle. And remember, that has a very specific name. That's called a coordinate covalent bond. Or you might have also heard of it as a dative bond. But that is an actual bond, and that forms the ammonium ion. So when we think about products here, one of the products that is formed is the ammonium ion. So NH4 plus 1 plus Cn minus 1. And really, we're done. There's no other ions that are going to be formed. Our net ionic equation is the same as the molecular equation, so I'm just going to save ourselves a whole bunch of times and just write same as above. And even more of a cheat, I'm just going to put a little thing like that. Okay, so same as above. So the molecular equation, the complete ionic equation, and the net ionic equation are all going to be the same because you're dealing with a weak acid, weak base scenario. The last situation is nitric acid and sodium hydroxide are mixed. So nitric acid is HNO3 plus sodium hydroxide, which we know is NaOH. Now I'm going to put definitely just a single arrow here because this reaction is most definitely going to completion. Water is being formed. And if I look at my 2 reactants, I have Na plus 1 reacting with NO3 minus 1 to give me NaNO3. And I believe it is already balanced. So now I'm going to go through and I'm going to label this. Well, HNO3 is a strong acid. NaOH is a strong base. Then we have liquid water, so we're not going to touch that. And NaNO3 is a strong electrolyte. So HNO3 is going to be able to ionize. NaOH and NaNO3 are going to be able to dissociate. So when I rewrite this, I'm going to write H plus 1 plus NO3 minus 1 plus Na plus 1 plus OH minus 1 yields H2O plus Na plus 1 plus NO3 minus 1. And now that I do this, I am going to go through and I'm going to cross out my spectator ions because they will not be in my net ionic equation. So Na plus 1, Na plus 1, NO3 minus 1, NO3 minus 1. I'm left with the hydrogen ion, the hydroxide ion, and water. So if I rewrite this, I will have H plus 1 plus OH minus 1 yields H2O. And that is my final example of showing a neutralization reaction, and this time between a strong acid and a strong base. So what did you learn? We went through the Bronsted-Lowry definition of acids and bases. We looked at strong versus weak acids and bases, talked about neutralization reactions in general, and then worked through examples of neutralization reactions, one between a strong acid, a weak acid, strong base, weak acid, weak base, and finally, strong acid, strong base. Need more help? Feel free to contact me. Have a great day.